Miss already marked for you. Okay, ready? Finish chapter 7, texture mapping. It's not enough time to finish. Is you didn't do your study. Didn't study. All the things we discussed during your tutorial, during your practical class. Okay, then I will give you back your paper during your tutorial class, your next tutorial class. So if your exam test not so good, then please do good in your assignment, and do all your practical exercise. Finish the practical exercise so that you can get more marks for your coursework. Okay, so today replace lecture is replace the Monday one, Hari Raya. So next week Monday also no lecture, Labor Day, holiday, and next Wednesday no replacement. We replace on week 30. Okay, week 30 Wednesday. You check your intranet. Okay, so next Wednesday no replacement lecture. We replace on week 30 after you submit your assignment. Okay. So today we do chapter 8. So two more after chapter 8, 2 more chapters to go. So total we have 10 chapters. Okay, chapter 9 is shadow. Chapter 10 is shading. Okay, chapter 8 is curve and surfaces. For chapter 8, no practical, your practical until lectures, and then one more last practical 8 is about chapter 9, shadow. Okay, shadow. Curve and surfaces. This one is not new things. We actually learned the quadratic equation last time when we draw circle. Okay, during practical 1. That is also one of the ways to create a curve. Okay, so another way to create curve, okay, in graphics is using splines. Okay, spline. Okay, spline is used to create a smooth curve and surfaces. Okay, what are spline? Okay, you can see the diagram here. Okay, so these are called spline. Okay, so you have a lot of nodes here. This dot, or this point, all this is called nodes. Okay, or control point. So then you use a functions. Okay, use function to connect all these nodes. Okay, in order to create a smooth curve. Okay, that's called spline. Okay. So use small sets of control point, or we call it nodes and a functions. Okay, that generate a curve. Okay, through those points. That is called spline. So with this one, that is allow you to create your complex smooth shapes without the need of manipulating many short lines, okay, of your polygon. Okay, rather than you use polygon, geolines, then you can use spline. Okay, functions. So just remember 2 things. So we need a set of points and then add a function to connect them. Okay, the function that we use here is the polynomial functions that you have learned last time. Okay, so with this then we can create all these curve. So since this chapter 8 curve is not in your practical, don't have enough time for you to do the curve practical, and more so is no need to implement in your assignment. Okay, so your robot. That's why when you design your robot, your miss asks you don't design like curve. Okay, too many curves like this. You see the human head. Okay, you just design using the shape, the polygon shape that we have learned. Okay, during your practical. Okay, the curve that you can use is only a circle, sphere, cylinder. Okay. That's why in your London Bridge, you miss say the string curve, no need to do. Okay, same for your robot. So with all these like Final Fantasy, okay, the hair, okay, of the characters, okay, you see a lot of curve. So all this is can be created using spline. Okay, the changing of the curve, okay, is by using a function, okay, to connect them. So for now, if you cannot do this lah with what you have in your assignment, okay, so all this animation, so you do normal walking animation enough, okay, no need to draw hair frying, blowing animation, okay. So all this with this spline, the introductions of the spline, then you can have okay, very good quality of the animations, okay, with all this curve changing of the line, all this, okay, can support with our NVIDIA graphic cards. So since 2008 lah. So spline I use to represent smooth curves and surfaces. So if you got used Photoshop before, got you Photoshop or not? Okay, so in order to draw curve, then you have to put the point there. Okay, all this point is called control point, and then you move this line. Okay, each of the point got this line. Okay, and you can adjust the okay, how the shapes of the curve. Okay, so in the same way, so we control using a function. Okay, the function that will generate this curve. Okay, that define how you connect those points. So we will see later lah, how many control point you put and what are the function that you use. Okay, with this one, then you can have a complex smooth shapes with curve. Okay, rather than you draw many short lines. Okay, like the circle and the polygon that we draw, the sphere. Okay, we are using the segment, short line segment. That's why you can see it's not smooth. Okay, when you use less number of triangle, less number of slices and stack, you can see your sphere and your circle is not so smooth. You can see the line. Okay, because we are using the short line. Okay, so the other way you can use spline, okay, which will only cost a little bit extra of the computational time. Okay, but it can create much more smoother curve compared to short line polygon. So why using spline? Okay, you can see here, this one. Okay, what you have learned before is you draw line, so you have point here, point 1, 2, 3, 4, 5, 6. So you use line to connect it. Okay, then you see this shape. Okay, this is the one, the black color line that connect all these red color vertex points. Then you get short lines. But with spline, then you can have a much more compact and smoother and more continuous. Okay, primitive compared to straight line and polygon. Okay, that's the advantages why we use spline. Okay, more compact, more scalable, more smoother, more continuous compared to short line polygons. Okay, and also your animation and collision detection will become more accurate, okay, simple and faster. Okay, and it will save the memories and increase the memory cache efficiency. So these are the benefits of spline. And rather than you draw many line segments, now you just use the function to connect the point to generate the curve. Okay, which is called spline. So the functions we can represent the curve and the surfaces. Okay, with these three types of representation. Okay, of the functions. Okay, you see this implicit, explicit, and also parametric. Okay, in order to draw this curve. Okay, we will go and see one by one the representations, the function representation, okay, of the curve. So you represent, okay, the most familiar curve in 2D, the most simple one. Okay, you represent it y. Okay, the relationship between your y and x. So if you're given a point y or x here, okay, you put in a function x, then you can get your y. Okay, y equal to a function of x. So if you see the equations, you got y here equal, and then functions of x or function of x and z. Okay, this one 2D curve lah. 2D curves, that you only have the x here. Okay, then this kind of representation we call it as explicit. Okay, explicit representation. So if it's a 3D, okay, 3D, okay, then you will have, okay, the z equal to functions of x and y. Okay, to define this 3D curved surface. Okay, it's the extensions of 2D. So you have the y of function of x and z of function of x, and combine. Okay, your z will be the functions of x and y. Okay, so this explicit representation. Okay, example of the curve is your polynomial function. Okay, with like y equal to a x squared plus a x plus a0. Okay, polynomial to represent this curve. And then this point, point 0, point 1, point 2, this is called node or control point. So you use this function to connect it to generate this curve. Where is your y here, your x here. Okay, this one last time you got learned in your MX polynomial function. Okay, so you take the equation, you see this representation type y equal to a function of x. This one function of x, you have your x here. So this is called explicit representation. Okay, you can given any functions, then you can get your curve. Okay, the types of the function will determine how your curve look like. Okay, not only the polynomial functions, your quadratic equations also okay, can be generate the curve. So for implicit representations, okay, you reorganize your equation, your functions, and then you put equal to 0 at your right side, okay, of the equation. Okay, you see whatever xy function equal to 0 or xyz equal to 0 for 3D, this one 2D. So you only have xy, a function of xy equal to 0. You see equal 0 here at your right side. This is implicit. Okay, implicit representation. Okay, this is the thing that last time you guys did in your MX lah. Like given the equation y equal to whatever, then you will organize the things, and end here you put 0 at the right side. Okay, this is called implicit representations. So all line segments can be represented by ax plus by plus c. Okay, your c here is the keturunan last time you learned before, x plus c. Okay, to draw a straight line. So at all circle you can use this x2 plus y2 minus r2. Your r is your radius equal to 0. So if it's a 3D, then not only have x and y, okay, you will have your z. Okay, so intersect with two surface, then you will get a curve. Okay, got example here. Implicit representation. Okay, don't have okay, implicit representation, you just see if it's equal to 0 at the right side of the equation. Okay, that is implicit. So from the implicit, you can also change it to explicit. Then you organize the equation, you move, and then only left the y is here. Okay, your y at the left side, and then the rest you move to the right. Then it will become explicit representation. Okay, the last type, the third types of representation require parametric. Okay, parametric is the most frequently used in your program. Okay, in your code. Okay, you split each of the spatial. It means you split your x, y, and z. You do calculation. Okay, by passing in the values. Okay, your arguments. Okay, that's why you have the parameter here. So each of them, your x, y, z, you have the functions of x to calculate and pass in this parameter u. Okay, your u got the range, your min and max here, then you trace. Okay, trace the codes, okay, of each of these x, y, and z. Okay. Okay, during you see this example. That is the point. Okay, point of view, this one, you pass in your parameters here, your argument. Okay, your xu, yu, and zu at time t. Okay, you see this curve. Okay, you have many points here. This is how you travel from S0. Okay, S here normally is your time. Okay, time 0 to time 1. Okay, then you use the function in each of these function. Okay, you pass in your u. For example, if your s here is 1, the 1 is here, okay, don't use 1. Okay, in the middle here maybe somewhere 0.1 or 0.2. Then you pass in 0.2. Okay, you calculate your x at 0.2, where's the value? Y at 0.2, where's the value? And the z at 0.2 is what the value? Then you put in here, that is your point P at this time. Okay, 0.2. Yeah. Okay, this is called parametric. So surfaces mean the 3D one. Okay, 3D one, you require 2 parameters rather than u. Now you need 2 parameters, u and v. Okay, you can see here, this is the surface, the curve. So any point here, okay, point here P. Okay, you need to pass in your x, your u, and then your v. Okay, here is 1, your y is 1. Okay, then you have to calculate what is the u here. Okay, at this point. So that's why it's actually further from this equation, same equation, but you just add in 1 more parameters. Okay, so you have uv here to calculate each of them. Okay, this is called parametric representation. You have parameter there, then you have to pass in the value to calculate each of the spatials x, y, and z. Okay, we already did this in practical 1. We draw the circle. Okay, the circle there. So we are using parametrics. Okay, parametric representation. You calculate your x and your y. Okay, on the curve, the parameters, the point on the parameter of the circle. Okay, using the r cos u, r sin u. Your u here is your theta. Okay, r is your radius. Okay, u is your angle. So the u is your parameters. Okay, so a parametric curve in the plane we explain in this way. So x is a function of x. Then you calculate by passing the parameter u. Okay, y. Okay, functions of y. Then you calculate using your parameter u. So the circle with the radius of r. Okay, we actually use this, okay, to calculate your x and y. Okay, so this form and passing you your u, which is your angle. So this is called parametrics representations of the functions, allow you to create your curve circle. Okay, circle already learned when we do Japan fact. So most of the curve that we draw is using this form, parametric form. Okay, we have to split 1 by 1 to calculate. Okay, rather than using the implicit and explicit. Okay, you change it to parametrics, then you use in your code. Okay, so these are the most popular methods. Okay, even though your miss didn't do in your practical, but you can find the code. You can find the codes online. Okay, how to create Bezier curve. Okay, the most common or popular methods to create curve. Okay, it's called Bezier curve. Sorry, this one got space. Okay, we will see what is Bezier curve. Okay, then Bezier curve got limitation. Then only we will have these B-spline curves and also the NURBS. Okay, NURBS mean non-uniform rational B-spline curves. So all these 3 methods is also to create the curves. So the Bezier curve is the most commonly used. Okay, because got limitation, then only these 2 is help to solve the limitations of Bezier curve. Okay, we will see what is Bezier curve first. Okay, Bezier curve also defined in the parametric form. It's also use the polynomial functions. Okay, to actually connect all these control points. So the Beziers, okay, this is a human name lah. Okay, he create this curve techniques or methods. Okay, he suggested that using the 4 data points, okay, 4 control points, then it will give you a cubic. Okay, we will see later what is cubics. Okay, and we actually connect them by interpolating the approximate derivative. Okay, the delta. Okay, so we have this algorithm from this Bezier curve. It's actually a recursive method. Mean inside there you actually is a for loop. For loop. So you just put your sigma, your sum. Okay, and start with 0 to n. Okay, how many points? Then you calculate using your polynomial functions. Okay, it's actually widely used in computer-aided design. Okay, to design the product with curve, as you can see here. Okay, we start with why it didn't move one? This is PowerPoint. Go move. I will move. See the one move one. This didn't move. Okay, this one didn't move. Okay, so Bezier curve definitions. So we use this equation. So 1 minus t. Okay, t is time. Okay, your n minus I, your ti, and your point I. So is sigma sum from I equal to 0 to n. Okay, from 0 to n, that is your control point. How many control point you have? N. So if you have 3 control point, 1, 2, 3. Okay, P0, P1, and P2. Okay, P0, P1, P2. So time you travel from 0 to 1. Okay, you calculate this interpolation. Okay, by using this 1 minus t, and then your time t and your point. Okay, at time t. So you get this. So you see the green color line. Okay, you get at time t, P0, P1. Okay, what at this point, and then P1 to P2, what at this point, and then you connect, interpolate, then you get the point at time t, which is the black color one. This is how to get your traverse of the curve. Okay, your spline. Okay, so this is called spline. You still remember this polynomial function last time? Okay, we start with simple one like 1 minus t. Okay, your n, if your control point is only 3, okay, 0.0. Okay, we start with 2.1. This one got 3 points, you get quadric. This is quadric. Okay, this is quadric. So if you have 4 points, 1, 2, 3, 4. Okay, then more calculation. Your this one will be long. If your n is more, then it's more. Okay, if your point are less, then less calculation. Okay, if more point, then you have to calculate. You see the green line. So you have to calculate the interpolation between P0 and P1, and then P1 to P2, okay, P2 to P3, that's your green color line. Then you have to calculate between, okay, I think we have later, your miss will explain. Okay, calculate one more, the blue color line, between the interpolation P0 and P1, and then P2 and P3, now need you draw the blue line to get the black color. Okay, that's interpolation. So this is the polynomial function. When more control point mean more calculation. Okay, we all these control point we can say it as a degree, polynomial degree, your n. Okay, if your n, okay, we actually advise you to only go up to 3. Okay, 3 mean you have 4 control point. Okay, see 4 control point. 1, P0, P1, P2, and P3. Okay, P0, P1, P2, and P3. So where you put your control point, so the curve also different. You can see the curve that you draw is different. Okay, so you are advised for your Bezier curve. Okay, you only go up to degree of 3, which we only have 4 control point. Okay, which will give you a cubics, and this is your polynomial of function point at time t. So 1 minus t. Okay, this one. Okay, 3 p0 plus 3t. Okay, 1 minus 3. Okay, 2 p1 plus. Okay, Okay, 3 T2 and then 1 minus 2 and then P2 and then your T3. Okay, P3. Okay, you don't need to remember this. No need to remember this formula. Okay, this one degree of 3 lah, so you come up here is 3. Okay, 3, 2, 1, 0. Okay, then P0, P1, P2, P3. Okay, that's a polynomial. So if you only have 2 control point, so degree of 1. Okay, degree of 1 means your n is 1. Then you will get a linear, a straight point, straight line. Okay, so your PT equal to 1 minus T P0 plus T P1. Okay, you get this. So if you have 3 control point, 1, 2, 3, this one degree of 2. Okay, degree of 2, you will get a quadric. Okay, quadric. This is called quadric equation. Okay, if you have 1, 2, 3, 4, 4 control point with the degree of 3, n equal to 3. So you can see n is 3, so 1 minus t 3, and then 1 minus t 2, 1 minus t 1, and this one 0, and then P0, P1, P2, P3. Okay, then you get cubics, 4 point cubic. So you are only advised to go up to degree of 3, mean 4 control point. Okay, to get a cubics. When the number of control point increase, like you've got 5, 6 control point, then it become more complex and more calculation. And more calculations, you see a lot of line, the green line, the blue line being drawn. A lot of linear interpolation that you're going to calculate here. Okay, between your line. So we start with the linear interpolations. Okay, the one that point 0 to point 1, only 2 points there. Very simple. Between the 2 points, just do linear interpolations. Okay, the one with the formula one is bad. Okay, so quadrics, also linear interpolation. So this one you only interpolate P0 and P1. Okay, see this one first. Okay, we start with degree of 1. Okay, degree 1, Bezier curve, which is got 2 control point. Okay, 2 control point. Okay, P0 and P1. So your equations are, you want to get the point at time t here. Okay, this one is 0, come here is 1. Okay, point at time t here, maybe this is 0.3. Example, if your t is 0.3. Then how to get this point? So it will be 1 minus 0.3, so it's 0.7 of P0. Okay, and then your 0.3 of P1. Then you get this point at time t. Get this point. Okay, your t is between 0 and 1. Okay, with order of 2, you just do linear interpolations. Define the 2 points in your polynomial function, then you can get your point at time t. Okay, that you calculate. Then you will get a straight line. Then this one is degree 1. Okay, mean your n, your sigma, and okay, your 0 to 1. That's why you only have P0 and P1. Okay, so we will, this one degree 1. So we will go to degree of 2. Okay, degree of 2, or we call it as order 3, mean you have 3 control points. Okay, then it will give you a quadric. So you want to get this point at time t, this one, okay, on the curve here. So it means you have to do 1 here first, P0 and P1, get the linear interpolation between these two, P0 and P1, P01, yeah. P01, so it's same like just now, 1 minus t of the P0 plus t of P1. So you get this blue color. Okay, then you have to do 1 here also, P1 and P2. Okay, P12 as time t, this one. Okay, so 1 minus t of P1 plus t of P2, then you get this one. Okay, then in order to get a point at time t, then one more interpolation here you have to get here. Okay, your PT, get from here your 0, 1 and your 1, 2. Okay, so you get this, your 0, 1, 1 minus t of your P01 and plus your t of your P12. Okay, so if you break it down, okay, then you will get your point t here. So it means 2 more interpolation, 1 here, 1 here, and then 1 more here. Then you can get this point at time t. Okay, so this one will give you a quadratic. Okay, so this one 3 control point with degree of 2. So next will be the cubics. Cubics degree of 3. Order 4 control point. Okay, more interpolation. So you want 1, 2, 3, 4. Okay, P0, P1, P2, and P3. Okay, you need to get a point at time t at the curve here. So first thing to do, you get your interpolate between P0 and P1. Okay, 1 minus t of P0 plus t P1. Okay, this one. Okay, then get P1 and P2. Okay, 1 minus t of your P1 plus t of P2. So you get this one. Okay, P1, 2. Then P2 and P3. So 1 minus t of P2 plus t of P3. Then you get your P23. Okay, get this 3. So after you get this, and this. Okay, now one more time. These 2. 1 minus t of P01 plus t P12, then you get this one. Okay, here it's called P02. Okay, after you get this one, then now you do one more here and here. Okay, 1 minus t of P12 and then plus T23, then you get this. Okay, then you have to do one more time. 1 minus t of this P02 and then t. Okay, here 0, 2, 3. Now you can get the point at time t. So you put in the equation. Okay, you see, more calculation. Then normally your miss won't come out this thing. Later you will die. This one is mathematics class. Okay. So from time, time is t to 1, 0 to 1. From pt 0 to 1, this is how you travel your spline, your curve, control point, and then you go here until here, your P3. Okay, then how to get your point here on the curve, okay, at time t is using your polynomial function. Okay, this one. Okay, the polynomial function actually last time you got already did in your MX. Got? So now you have to implement in your code. Okay, so we just want to see the pseudocode lah. We have the code there. So this is the cubics. So more interpolation, you can see green line and also the blue line. Okay, so this order of 4. So you only ever go up to here because when the numbers of point increase, more calculation and more complex already your curve. Okay, later we'll see the limitations. Wait, just now your miss got skipped here. Okay, so we have the linear picture is a linear interpolation between the 2 points. So the quadratics is a linear interpolation, okay, between the 2 lines. So 3 points. So just put in this equation pt. So 1 minus t. Okay, 1 minus t p0 plus t P1 plus T, then 1 minus T, P1 plus P2. So the cubic is a linear interpolation between linear interpolation. One more then, between linear interpolation. Because order of 3. Okay, 3 linear interpolation. That's cubic. Okay, if order of 1 is only 1 linear interpolation, there is only 2 points. Okay, 3 points, then you got 2 linear interpolation, order of 2. Okay, so you can have generate many different types of curve. Depends on where you put your control point. Okay, you move your control point, then the curve also will change. Okay, that is also one of the limitation. So we see already degree 3. Okay, and this one Bezier curve. Okay, this is the code. Okay, you can try lah. You can put inside your Visual Studio to draw. Okay, so you will use while loop. Okay, while loop, your n, you see order. Your n equal to 1, 2, 3, 4. N 1 means 1 control point. Okay, 2 control point, 3 control point, and 4 control point. So while n is more than 0, okay, then inside got for loop. So you have to calculate one by one. I equal to 0 to n minus 1. Then put in your polynomial function. Okay, your point I equal to 1 minus t, point I plus t, point I plus 1. Okay, if your I is 0, then your P is 1. Okay, then you n equal to n minus 1. So it's in a while loop until your n is equal 0. Okay, because this one is only more than 0. Okay, then you return your point. Okay, this is the Bezier curve pseudocode that you can put in the algorithm, the code that you can put into your program to do the calculation, to generate your points. Okay, your point here is your vertex. Your vertex. Okay, let's see the limitations of Bezier curve. Okay, just now you guys already see already. You see, when a lot of control point, we mean more interpolation. More interpolation means more calculation. You have to calculate the interpolation between more points. Okay, this is one of the limitations. Okay, the point become complex and a lot of calculations that you have to do in order to generate the curve. Okay, and another one limitations of Bezier curve is no longer control. It means that if you drag your point, your control point there, you go and change. Okay, then what happens? Your whole curve, the shape will be changed. Okay, except the endpoint. So why you need to move the point? Because we need to do affine transformation. Okay, you need to do your TRS. You have the curve there. You want to move your curve. Definitely, you will move the point. Okay, if one of the point you don't move correctly, then your whole curve look different already. Okay, that is called no control point. So it will limit the amounts of flexibility when you do your transformation. Okay, so this is also one of the limitations of Bezier curve. Okay, that's why we have some solutions to solve these two limitations of Bezier curve. Too many control point. Okay, more calculation. So if you have a long curve, so you are advised to break it down. Okay, break it down to small degree or controllable degree of Bezier curve. Okay, which is 4. Okay, 4 control point, you break down to 4, 4, 4, 4, 4. Rather than you have one curve with 16 points, you can have 4 curves with only 4 control points. Okay, then you connect. Okay, connect those curves. Connect all the small curve. Okay, the Bezier curve that you create. Okay, so for the connectivity, the continuity, we say the concept of continuity to connect your curve. Okay, we have four
你们要
continuity.
extend
Okay, the first one is no continuity, mean the two curve. Okay, this one got 4 point, you see, you break down to 2, 4, 4. Okay, for 4, the two curve didn't connect. Okay, no continuity, the curve do not meet at all.
这
Okay, this is called no continuity.
显不出去。
Okay, then we have C0. Okay, C0 continuity. So just nice that your endpoint of your first curve here is meet at the starting point of your next curve. Okay, then it somehow connect in terms of position. Okay, so two curves will meet. Okay, will have the positional continuity. But this one, your connectivity here will look very sharp. Okay, the connection point here will look sharp because they just meet at the position. Okay, this is called C0. Okay, positional continuity. So for C1, okay, not only they meet at the same positions. Okay, they also have the identical tangents. Okay, what is identical tangents? Okay, mean the direction. Okay, the direction side, this one go down, this one also go down. Okay, you just have one go down and then this one just connect but it suddenly go up. Okay, there's only C0 position. Okay, this one go down and then you see the direction same. Okay, that is called the slope. Okay, the tangent is the slopes of the breakpoint. So it just nice this slope of the breakpoint are same. So that's why the joint here you will look smooth. Okay, the curve will join smoothly at here. So not only have position continuity, it also have tangential. Okay, continuity. This is called C1 continuity. Okay, so the last one is C2, and this is the best. Okay, the best continuity. Okay, not only the position same, tangential same, position same. Okay, it's also same curvature. Okay, the curvature also same. Okay, what is curvature? So the curvature means the rates of the changing of the tangents. Okay, mean the changing of the direction between the two curves are look
这个是另一个结束。
Okay, so it just looks like a one line. You didn't see it's actually it's a two
哎，等下，
different line that actually connect smoothly and their direction are same. Okay, the changing directions of the curve are same. Okay, this is called curvature. Okay, which will give you the best continuity. Okay, so we have 4 types of continuity. So no start with no continuity. Okay, then we have C1, only position same, just meet only very sharp. Okay, then C1, okay, meet position and then it tangent direction same, so it joins smooth. Okay, C2, okay, not only the direction same, position same. Okay, the changing of the direction, curvature also same. So we'll give you the best continuity where you can see the whole curve. It just look like one curve. The two curve join smoothly, just like one curve. Okay, so that is continuity. So break it down to solve the first limitation of Bezier curve. Break it down to a controllable degree, 4, 4, and then you connect it using the continuity here. Okay, the second solution, this one is to fix the second limitation of Bezier curve, which is the no longer control. No longer control. When you change one point, then the whole shape will change. The whole curve will change. Okay, so we can have this something we call non-uniform. Okay, rational D-spine. Okay, NURBS. Okay, it's actually to define or to control. Okay, how your objects shape, okay, will be changed. So it still use the polynomial function, okay, but in this 1, it will use 2, and then we add in the weights, the weight. So what is rational? So object that you define using formula, okay, max formula. Okay, other than one polynomial that we saw in the Bezier curve, now you have 2. Okay, 2 will we will see the formula later. Okay, 2 polynomial functions. Then for the B-spline, basic spline. Okay, you need to make sure it is under controllable degree. Okay, don't go up more than 4. Okay, so we will add in the W. Okay, the weight here. Okay, so this is the NURBS. Okay, we already modify the polynomial functions here to get the point at time t. So previously Bayesian curve is only used one polynomial. Okay, now you use 2. Okay, and you add in this W here. Okay, your W is your weights. Okay, so NURBS will use the sequence of the weights to control. So when you move the point, okay, we don't move the point at time t, we actually will just change the value of the weight. So the rest of the thing will still be the same. Your curve will be still the same, only move using your weights, your W here. Okay, W from 0 to n. So each of the control point. So to control your control point Pi, okay, 0. Your I is from 0 to n, so which will control each of the individual control point using this weight. Okay, so you have your polynomial 1 and then you divide by your another polynomial 2. Okay, and you control add in the weight. Okay, this is called NURBS. So with the implementations of NURBS, we will see one example of NURBS later at the end of the chapters, which is called conic section. Okay, how you actually adjust the W and then you can get different shape. Okay, so the advantages of using NURBS, so you can have more flexible, more controllables. Okay, with invariance of this your affine transformation. Okay, your TRS. Okay, so save the computational overhead that you have to transform every single point of the curve. Now you just have to adjust the weight. Okay, just pass in different weight, then you can. Okay, you can do the TRS. So it will be more control over the shape of the curve, and you can just change the weight vector for each control point in order to move or to transform the curve. So we have this conic section. Okay, conic section here. And now you rebuy your maze. Already 5. Want to finish? Can finish? 5. A little over 5. Emma, you want me stop here lah? Okay, we have the last part is the conic section. Okay, next Monday got no. Next Wednesday also no. So next week no lecture at all. Next week Monday and Thursday holidays. Labor Day and Vesak Day. Also no tutorial. I see you practical only some of you. Then we continue next Monday. Yeah, torture you lah. Later you see your. Okay, so that's all. Okay, the conic section we leave it for next week. Okay, that's all for today. Thank you, class. Okay, this one no need for your assignment. That's why okay can push on week 30. Next week holiday do assignment. I mean don't disturb you. Don't repeat my class.
Disturb me.
Next week. Okay. Next week is finish assignment week. Yeah. Next week is week 12 already. Week 13 Monday you have to
Means you
submit.
no extend
No extension right.
until Friday, week 13 Friday.
But just now I